There we go. Oops. So if we if we do 2 to the 4, well, we would call exponent 2, 4. That would go into our recursive case. So it would go into that else statement, and it would do return, well, 2 times exponent 2 to the power of 3. So before that function returns that called 2 to the 4, it has to actually compute 2 to the 3. So we would do another function call. So this is another function call, so I put it here on the stack to indicate that the other one is still active. It's waiting for this one to complete. So right here in the gray text, that is what we're trying to compute. And every box is a new function call that would have its own local variables. In this case, it would be b is 2 and n is 3. So to evaluate exponent 2 to the 3, that would go into the recursive case. So we would get 2 times exponent 2 to the 2. Okay, well, now we have to figure out what exponent 2 to the 2 is. That is another function call. So we call exponent 2 to the 2. Then that gets into the recursive case again. So we get 2 times exponent 2 to the 1. Then it gets kind of boring. So then we do have another function call with exponent, or 2 to the 1. And then, well, that is 2 times exponent 2 to the 1. So we would call that. And then mercifully, this is our base case. So in this case, n is equal to 0. So it would just get a 1. So it would return 1. So the function that called it gets a copy of 1. And this whole thing kind of unravels itself. So then it would return. And then in our 2 to the 1 function, we would calculate 2 times 1, which is just 2. And then that is the result for 2 to the power of 1. So that would get returned for this function call. Then we have 2 times 2, so that would be 4. So that's 2 to the power of 2. And then it would get returned here. And then it all kind of unravels, right? So now here, that 4 is returned. It gets a copy of it. So then we would do 2 times 4, which is equal to 8, which is thankfully 2 to the power of 3. And then here, well, we would return 8. So then we would get 2 times 8. And then we'd get finally our final answer, 16. So lots of steps. It would be, in that case, what, 5 function calls? But we got the answer. In this case, a for loop would have probably been less confusing. But is there any questions about how this worked? Because it's going to get weird once we get Fibonacci going. So we're all okay until it gets slightly more strange. Okay, so let's go ahead and run it, make sure it works. So here's that exponent code. So here I just have my base case and my recursive step. Oops. And then if I go ahead and run it, I could do to the power of 4, something like that. I get 16. Seems to work. To the power of 5, 32. But if we implemented this with a loop, I could probably do like 1 to the power of, I don't know, some large number. And that would be fine. It would just might take some time to execute, right? Well, let's see what happens here. So if I run that, I get a segmentation fault. Crap. Well, I didn't even use malloc. How in the blue hell do I have a segmentation fault? So one of your steps might be, okay, well, I'll use Valgrind, and then I'll see. It says, okay, I have no memory leaks. I didn't allocate anything. So what happened? So you try and scroll up, and then you get a bunch of random text that's probably not so readable. The only thing that you have any hope of reading is this thing called a stack overflow. So we know that kind of what a stack is. It's where all the local variables are. And in this case, the stack overflow means basically it ran out of memory. So this is a very common thing you can encounter once you do recursive functions, because if there's too much recursion, we essentially just run out of memory. So I did, what, to the power of like 1,000,000 or something like that. So that would mean that, 1,000,000 called 99999, called 99998, called that, called that, called that, called that. And, well, every function that is active has a b and an n at least, so it has 2 integers. So I essentially just ran out of memory because every function call needs its own variables. So that is what a Stack Overflow means. Basically, just I ran out of memory. So again, like I said, every time we call a function, that function gets its own copy of the variables. In C, they store local variables on the stack. So if there's many active functions at once, so there I did 1 to the power of a lot. So if I was to draw that out on the slide, I would run out of room because it would just call itself over and over and over again until it actually ran out of memory. So running out of memory for local variables called a Stack Overflow. That is the name of the helpful website that you can get questions and answers to for programming questions. So they named it that because, well, this is a common enough error that is really hard to go, and it means you have screwed something up, because usually people get to recursion and then things start screwing up, and then most programmers see Stack Overflow a lot when they are starting out. So common cause for Stack Overflow, more likely than not, is infinite recursion. So it's similar to an infinite loop, except in an infinite loop, just takes a lot of time. It doesn't actually need more memory each time you go through the loop. For recursive functions, it needs more memory essentially every iteration of the loop if we were thinking about loops. So we can actually likely run out of memory before we run out of time. So this is far beyond the scope of the course. So don't worry about if this part doesn't make any sense. But there are like certain forms of recursion that can be optimized more easily. So we can rewrite some functions to use what's called tail recursion. So it's a special recursive function that just has a single recursive call in the return statement. You do not need to practice actually rewriting this. This is mostly for performance. So if we modify exponent, well, we could create an exponent that takes 3 variables. So before we just returned a number. Well, like in our recursive case, we did like 2 times the recursive function. So if we want to be tail recursive, we can't do that. So we create another variable here that's local to the function called accumulator that just keeps track of the current value. So in our base case, instead of returning 1, we just return whatever the final value we have is. So it would do like 2 to the 2 times 2 times 2 times 2. If we did 2 to the power of 4, then eventually it would be 16, and then we just return 16 at the end. And this is our recursive case, so we just do the calculation with the accumulator, so we just multiply b by it, and otherwise it looks the same as before. So if we want to keep exponent looking the same, well, we have the base and the n, and we can just return exponent written in this tail recursive manner by giving the accumulator 1 and then giving b at the end. And the only reason why I show this to you is because compilers can optimize this function. So if it's recursive, a lot of people don't like writing recursive functions because, well, it wastes a lot of memory, and you can get into the Stack Overflow issue, where if you just wrote a while loop or for loop or something like that, that would work better and you wouldn't have that memory issue. So it's actually guaranteed that compilers, and you'll learn this in like 4th year whenever you get to compilers, but it's guaranteed that compilers will optimize this away. So it will optimize away the recursive call and just convert that whole function into essentially a while loop. So it would convert it to this for you. So just start off int x equals accumulator. So in our case, we set it equal to 1. and then it would just go while n is not equal to 0 and just do the recursive step over and over again. So now our code doesn't have a Stack Overflow, doesn't have that issue because we're not actually doing recursive function calls. We let the compiler optimize it away for us. And in this version, maybe you can argue that the recursive one was more readable, so you'd rather have it than this. But for calculating an exponent, probably just a while loop is going to be much, much, much easier to do. But it's good to think of things recursively because, well, some solutions lend itself better to recursion than others. So let's rewind a bit and see what happens when we call fib of 4. So this one is a bit different than the exponent, where in our recursive step, we return fib n minus 2 plus fib, or fib n minus 1 plus fib n minus 2. So we do two function calls here. So if we actually want to evaluate something like fib of 4, turns out it's going to be a lot of work to understand how your computer actually executes this code. So gets a bit ugly. So if we evaluate fib of 4, well, we call fib of 4, and again, I'll just write in the gray here what the function is supposed to be computing. So it's supposed to be computing the 4th Fibonacci number. So in order to compute fib of 4, well, that's the recursive step, right? It should return fib 3 plus fib 2. So we have to do these function calls. So C will go ahead and it does function calls in left to right order. Don't have to know that for the course, but in order to figure out how this actually works on your computer, it's important to know what happens first. So we will do this function call for fib of 3. So we'll do that function call. It'll get its own copy of n. And we do fib of 3. Well, that goes into the recursive step. So it would return fib of 2 plus 1, right? Then, okay, now we need to call fib of 2. Okay, so we call fib of 2. Fib of 2 is equal to fib of 1 plus fib of 0. Mercifully, when we call fib of 1, that is thankfully our base case, right? So it would immediately return 1. So that whole thing would evaluate to 1. And then it would return and give us the value 1 back for, in this case, fib of 1. So it returns, and now, oh no, well, we still have to find out what fib of 0 is, right? So now we have to figure out what fib of 0 is. So that is another function call to figure out what fib of 0 is. That mercifully is another base case. So that just gets the value 0. So it returns. And then we can finally figure out what the second Fibonacci number is. So it's 1 plus 0. So it would figure out that that is 1. Okay, great. So that was figuring out what fib of 2 was. So that would return the value 1. Okay, well, now we have to do the other half of it. Now we have to do fib of 1. Okay, well, that's another function call. So we call fib of 1. Mercifully, that is another base case. So that just returns 1. And then, well, that returns 1. So then we can figure out what the third Fibonacci number is. So it's just 1 plus 1. So that's 2. So now that returns, right? So that is fib of 3. So that returns. Oh, God. But now we have to figure out what the second Fibonacci number is. So that is another function call. So this whole thing kind of goes again. So we have fib of 2. Okay, well, that's a function call. Oh, that's our recursive case. So we would return fib of 1 plus fib of 0. Ugh, okay, so then fib of 1, that's another function call. Mercifully, that's our base case, so that's just a 1. So then that would return, okay, yay. So now we have to figure out what fib of 0 is again. So fib of 0, okay, that's another function call. That goes to the base case. Mercifully, we know it's a 0. Then it would return. And now fib of 2 is done. So we get 1. Then that returns. Now we can finally figure out the fourth Fibonacci number, which is 2 plus 1, which is 3. Yay! Wasn't that fun? So, any questions about how that works? Other than it seems like it takes a long time to figure it out. So, let's see. So, here is that implementation. And just as a review for the last one, instead of just asking and doing scanf, I'm just using that other version of main that takes another argument that I can type to it just because I don't feel like hitting enter 2 times. So I check that there's 2 arguments and then use AOTI to convert the first one to an int. And I assume I'm being nice to it. I'm just going to print the result of calling Fibonacci on whatever that number is. So if I call fib of 4, it was a lot of work for us to figure out all of the function calls and how they work and who calls what and what values and when do they stop. But computers are fast, so it just gets 3 quite readily and works. So if we computed 10, we get 55. Turns out it grows pretty fast. 20, we get 6,000, something like that. Seems to be pretty fast. Computers are quick. But if we get 40, you might have noticed that took a little bit of time. Maybe 44. 44 took a bit of time. It was a bit slow. And also for this one, we could just write it in a for loop too, and it would be way faster and way easier to actually compute. But again, we're just kind of practicing recursion, even though it doesn't really make sense. This would be a lot easier to just do in a for loop. So, any questions so far about evaluating that? Yeah?
Is there any way to know how much slower it'll get depending on how many recursive steps you have?
Yeah, so the question is, do we know how much slower it will be depending on how many steps it will get? So you can kind of guess it's going to get like, in this case, almost 2 times slower every time because, well, if I have to compute 44, that means it has to compute 43 and then 42. And then if I have to compute the next one, well, then I have to compute 44, which is going to take as much as what I ran before plus a 43. So not quite 2 times slower every step, but gets up there. So if I do like 45, probably pretty slow. Yeah, oh, crap. So, oops. So, if I do 44, 1 Mississippi, 2 Mississippi, it takes a bit of time. If I do 45, 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi. Okay, so took about twice as long because essentially it has to calculate everything it had to do before and then do it all again for the next number. And then you might imagine this might be like exponential. So I have to compute one side and then the other side, and then I have to do it again and again and again, and it's kind of a pain. So that leads us to our next thing, which is we can whoops, wrong thing. Leads us to the next point of, again, so this part, again, is beyond the scope of the course. For this course, just writing recursive functions is good enough for us. We'll get some more practice as it goes on. But just so you know, you can significantly speed this up without actually changing it from being recursive with something called memoization, which is just a fancy word for caching. And caching is just a fancy word for just saving values that so you don't have to recompute them. So even with calculating fib of 4, well, we had to calculate like fib of 2 a lot of times. And we had to calculate fib of 3 once, and fib of 2 a bunch of times, and then a lot of, well, we didn't have to calculate the value for fib of 1 or fib of 0, but we could change our program a little bit so we don't have to go ahead and recompute them over and over again. So one optimization we could do that you could probably implement right now, but you don't have to for this course, is just I could just remember some old value in an array, and then if I've already calculated that value before, I can reuse it again instead of recomputing it. So this one took, I almost counted like 5 Mississippi. It was really, 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 really slow. So I wrote another version of it that just saves the value that is computed already. So it just reuses it over and over again instead of doing the whole recursive nonsense over and over again. And if I run that, whoops, that is the same function. So if I run my optimized version, boom, look how fast that was. So there are some techniques you might employ that some problems will have to be recursive and they might be slow, and this is one technique to speed it up. Again, just something to think about. Don't have to do that in the context of this course at all, but it will come up, probably in your next programming course. So, recursive functions are basically just another tool. Some problems are easier to think about recursively, especially if you're like more of a mathy person that likes proofs and all that stuff. It was never me, so it took me a bit to figure out this recursive thing. But some problems, believe it or not, are actually easier to solve recursively. So it's good to get some practice trying to get yourself into that mindset. So typically, recursive functions are going to take more space to execute. Tail recursive functions can be optimized. Again, don't have to know that for this course, but in your career, that might be a good thing to know and try to write for. So it's important to practice so you can go ahead, identify these types of problems, and be able to solve them. And the main two things are, given a problem, you probably want to identify a base case, so something you know a value for given one of the inputs, and then you also want to create the recursive step. So you want to solve the problem in terms of itself. You want to solve the problem in terms of a smaller version of itself. So typically it'll be you do one thing, like you just take one step and solve that. So let's think about that for more practice. Can we write a recursive function to calculate factorials? So sit, think about it for a few minutes, and then we will try and come up with the code ourselves together. So we're trying to calculate factorials, and like for an example, well, the 4 factorial would be 4 times 3 times 2 times 1. So take a minute, think about how you would solve that and write that as a recursive function. So these are the types of things that would be on exams and stuff like that. Like for this course, most of the problems you'll see you can probably solve with like a while loop or something like that because, well, you have to be able to write them during an exam, and recursive stuff takes practice. So generally you'll probably get some question on the file will be like, solve this problem with a recursive function. All right, I'll give you a few minutes for that, and then we'll try and think about what the steps would be. All right. Yeah. I can't hear you, sorry. Okay, so I'll take you first, so you will start half of it. So the first thing we need is a base case. That's been answered up there. So our base case would probably be, well, if we're computing like n less than 2, so if we're computing the factorial, we'll assume no negative numbers. If we're computing 1 factorial or 0 factorial, well, they're defined as just being the value 1. So that is our base case. So I'll get someone else for the recursive step. So that is one thing we need. So the other thing we need is our recursive step. So anyone with the idea of what we should do in the recursive step. So how do we solve factorial in terms of itself? Yeah.
Just return n times factorial of n minus 1.
Yeah, so my recursive step, I could write in an else here or return, doesn't really matter. So in terms of solving it in terms of itself, well, let's assume the number is 4. So in order to calculate 4 factorial, well, that's just the same as doing 4 times 3 factorial. So if we wrote that in terms of C function calls, our recursive step would be to return n times n minus 1 factorial, which would just be factorial of n minus 1. Everyone agree with that? So turns out this one might be easier to think about than doing all the for loop and everything like that. So if we do, I don't know, 4 factorial, 24, 10 factorial, some large number, seems to work. Cool. That was faster than I expected. Any questions about that? Yep. Oh, no. So the question is, can I do a recursive macro?
Yeah, like, so it's like, for example, like power event, right? You, like maybe it's just so when it wraps, because like it happens like before compilation, basically, right?
Yeah.
Could you like maybe like 2 comma 5, like you can pass it to the macro and just gives you 2 byte.
I'm not sure if the C preprocessor lets you define recursive macros. I'm actually not sure. I don't think so. It's fairly straightforward and simple, and that would probably complicate it. So I don't think you can, but can do recursive functions, no problemo. So any questions at all about factorial? All right. Wow, I outdid myself. So here's the solution for you. So same thing we developed. So important things. So we will get a much more complicated example in the next lecture. I even have fun toy props that I can bring in. But for this one, just remember a recursive function, just a function that calls itself. In order to think about the problem, well, your solution needs 2 things. So you need a base case, which is basically a simple solution you know. So something you know how to do that you don't have to think very hard about. And then the other one is your recursive step that you'll have to develop, which just solves the problem in terms of a smaller version of itself. So the idea here is, since it's a smaller version of itself, you're making progress each step you take. Eventually, you will hit the base case, and then you can just let your computer solve it for you. So yeah, we're really 13 minutes ahead. All right, cool. I like it. All right, so we'll just stick around for the remaining 13 minutes, but just remember, pulling for you. We're all in this together.